So I'm going to be kicking it off and talking about some of the agenda for the day and some of the focus areas. Then Andras would be jumping in for the technical portion of how the theory and the background behind it and the proof of concept that we've done to basically highlight some of the techniques that can be used to get some advanced thermal testing and characterization for pluggable I/O primarily. So in terms of the focus areas that we have today, I'm going to start it off by talking about some of the challenges as it relates to pluggable I/O, because with the incremental speeds, exponentially increasing speeds that we are seeing, thermal management for I/O has been a challenging bit in the last couple of years. So I'm going to be talking about some of those challenges and how those make the current testing and characterization approach perhaps not the best approach to do the calibration for those models. Followed by that, we'd be talking about some of the limitations of that approach, and then Andras would be helping us talk about the thermal transient testing and the structure functions and the proof of concept that we've done to basically show how this technology can be used in pluggable I/O to do some of the calibration. And then we would have a strong call to action where we'd be talking about what our plans are in terms of next steps for this. So in terms of the overview, just last year, we were here talking about how we have basically introduced the tall small form factor, which is a height increase from the small form factor, which again, one of the key drivers for that was the thermal management of the pluggable I/O. So essentially emphasizing the point that thermal management for pluggable I/O is becoming an increasingly important topic, and now for a lot of the designs that we do, it's pretty much a three-legged stool, where it's mechanical, SI, and then thermal is now the third leg. So with that said, high semiconductor junction temperatures, as we all know, lead to reliability issues and ultimately failure that we see in our performance of the transceivers. That makes it really imperative to understand the conduction path for the thermal design to basically make the best decisions to efficiently do the thermal management for not just the pluggable I/O, but the entire system and the architecture. A simulation-only approach that is perhaps used today, or a brute force approach where thermocouples are probed and then there's a sweep through like permutations to get the right calibration, is perhaps not the best approach in a time when thermal characterization and thermal management is becoming increasingly critical. For the purpose of this discussion, we would be focusing on one of those parameters that I'm sure has given us a lot of trouble in terms of measuring it, the thermal contact resistance between two metal-to-metal contact, like which in this case would be optical module and the riding heatsink. So that is what we would be talking about today in terms of how this new approach we're suggesting enables a pathway towards that. So I'll start off with some of the thermal challenges that we have with the approach today. So the traditional approach that is used today is basically a thermocouple is used on specific areas of the device under testing, and then simulations are run, and then it's sort of a permutation approach where you sweep through and you change the thermal characteristics, and you get the right sort of thermal characterization. So I would say the smaller disadvantage of that is that it's a tedious approach. It takes a while to calibrate your models and characterize them and correlate them. But the bigger issue that we see in a time when thermal management is becoming so critical is that what at least we see in our industry is our vendors are mixing and matching the models, the thermal models. So we have standards set for electrical, the IEEEs, we have standard set for mechanical, the MSAs, but there's no standard for thermal models or thermals, right? Which basically, the way that the thermal testing is done right now, it's more of a subjective approach because there's no set standard to that. The downside of that really is the misappropriation of thermal characteristics eventually leading to non-interoperable thermal models. As an example, what I could basically talk about is, let's say we are thermally calibrating our device, calibrating our assembly using a cage, heatsink, and a transceiver. So we can calibrate it, but at the same time, there's a risk. We don't know if our transceiver has been accurately calibrated, so it might very well be that we are changing, let's say, the dry contact resistance to match the temperatures, but in reality, what needed to be correlated well was the transceiver. So what that does is it gives us a nice correlation for that specific assembly. However, when you take that cage and heatsink and plug in a different module or a transceiver, the correlation does not hold. So the misappropriation of thermal characteristics is one of the biggest limitations of the methods that we have today in terms of calibration and correlation. Again, With the thermocouple approach and the IR camera approach, we do not have the junction to case, visibility on junction to case, visibility on the resistance and capacitance layers, and that basically limits our accuracy and consistency. So that basically, I've talked a little bit about the challenges that we have today with the current approach that we have. Now, I'll give it over to Andras to talk a little bit about what our new approach is and how it helps us get those parameters more accurately and consistently.
Thank you very much, Hasan. Hello, everybody, also from my side. Let me just move to the next slide, please, and talk about an approach which we chose to help with these measurements, and that's thermal transient testing. So when you look at the previous slide and think about thermocouple measurements or infrared camera measurements, all of these allow you to get some surface temperatures of your components or parts you're trying to test. The approach we are taking with thermal transient testing is looking at the semiconductor component inside packages or assemblies, and we're measuring the junction temperature of semiconductor components. If you look at the measurement approach, it's fairly simple. We start with forcing a power step on the component. So you can see in the slide P1, which is pretty much the hot state. We try to provide as much current as typically used during the normal operation of the component. And P2 is a low, we call it sensor power level. This is a small bias which is needed to get a voltage on the semiconductor component we're trying to test. Because the main point of the test is making use of the semiconductor component's temperature sensitive, typically voltage parameters. So once we can identify and bias that parameter, we're able to capture its change as a result of the power step and get both temperature information and also structural information of our package or assembly or subassembly. The idea behind this is to get those characteristic thermal resistance and even thermal capacitance values which would describe the different layers of the structure. A little bit talking about the mathematics behind this. So what we are doing, you saw that power step in the previous slide. The whole idea is if you have a package or a system which, let's start with a known characteristic. So let's assume we know our component. If we know our component and if we know our excitation, our powering, using a so-called convolution integral, we could actually calculate the response of that system to the excitation. In case of the problem which we were trying to solve here, we have a system which is unknown. We have a powering which we know, and we are capable of measuring the response of the system. So if we do the inverse of this so-called convolution or do what we call deconvolution, we're able to get the system characteristic response of the package or subsystem we are trying to measure. If you look at it down here, we basically start off with that thermal transient response. And what we do mathematically is we try to get a couple of hundred thermal resistance, thermal capacitance elements which would have the same response as what we have measured. And if we organize them in a specific way, which is called the core thermal model of impedance, we can get the capacitances and the resistances ordered in a way that they will be also descriptive of the thermal structure. So as the heat is flowing through the structure, as the resistances start to grow and the capacitances develop, we are capable of capturing that with a single measurement. And finally, we can just take a plot instead of a full set of R's and C's. If we plot the capacitances as a function of the resistances in this chart here, we can get what we call a structure function, which you will immediately see in action in a slide or two. So very briefly, what was the component we measured? Hasan provided a picture of this Pluggable IO module, and we had the ability to actually rip it apart. And if you look at the sample here, the only difference we made, we soldered electrical wires to certain terminals of the semiconductor components we wanted to measure, because the measurement is done electrically without really changing anything in the thermal structure. And then we connected it to our instrumentation. One thing which is very important, besides electrically biasing the component, we also need to provide a stable thermal environment during the measurement, and that was done using this thermostat and the insulation around it. Getting to some results, so you can see down here we powered the component with 2 amps. That generated that power step. When we went to the low power, we just switched down to 50 milliamps. We did the measurement for 300 seconds. That's kind of capturing the data after the power step. And here is a typical response, which you can see. So roughly from 21 degrees C ambient, we went to approximately 30 degrees C. It's not a big change, but it's enough to understand the structure itself. This is the cooling response of the package for this power step. And if you look at the very beginning, there is a small wiggle. This is actually the electrical switching characteristics of the semiconductor component, which we also measured and we had to deal with. Here is a cartoon of the structure which we were measuring. And the first measurement, boundary conditions are very important. The first measurement was a measurement of the PCB board. As you could see it, we put cold plates to both sides of the components, and we didn't use any thermal interface material between the components and the cold plate. So for that, we captured this RC network model. Again, capacitance is on the vertical axis, R's on the horizontal. And we got approximately 7 Kelvin per watt junction to ambient. If I try to analyze this function here without really knowing what's inside, it would be difficult. So what we did was we made boundary condition changes. These yellow areas highlight the changes. We put thermal interface materials between the pads and the cold plates. And that created this bifurcation point at a little bit less than 3 Kelvin per watts. So this is the junction to pad thermal resistance of the components which we measured. And then the overall thermal resistance decreased by approximately 2 Kelvin per watts with this step. Now, as a next step, we put the chassis on the PCB board itself. And what we did was we did a very similar comparison. So if we just put the chassis, we would get an increased thermal resistance here. So from approximately 5 Kelvin per watts, we went back to roughly 6.5. If we put thermal grease between the chassis and the cold plate, we can actually get some reductions. So the green curve would show you that there's a second bifurcation point and there is an additional reduction in the thermal resistance. Now the question of this exercise was to figure out the contact thermal resistance between the chassis and the external heatsink. So in order to do that, we needed to take 2 steps. We needed to figure out the thermal resistance where the chassis ends and the cold plate starts. And we needed to see the thermal resistance from the point where the heat starts spreading inside the cold plate. So that's basically the difference between the two should give us the contact thermal resistance we were looking for. We achieved the first one, so understanding where the chassis ends using this dual interface method you can see here on the left. And that was roughly 4.5 Kelvin per watts. What we did after, we shifted the green curve to the right, and we overlapped the end of the 2 curves. You see a sudden increase in the capacitance at this area. That's actually where the heat gets into the cold plate. If I mark these 2 lines on my original function, that would carve out approximately 1.07, 1.08 Kelvin per watts. And this is the region exactly which stands for that contact thermal resistance. Now, understanding the geometry of this assembly as well, we were able to calculate the contact resistance per area of the component, which was pretty much in line with the expectations from Hasan and his team in Molex. Let me hand it back to you here.
Sure. Thank you, Andras. So I can talk a little bit about the benefits of the suggested approach that we have today. So I'll start with something that is perhaps not stated on the slides. And the biggest benefit of this approach is it gives us a path to measure what was previously the unmeasurable. So putting thermocouples at a contact and getting the exact contact resistance was something that was not possible. Having a way to measure that, quantify that through an experiment rather than brute forcing it is what I would say one of the biggest benefit of the suggested approach. The other thing, what it does is it basically addresses the concern that I highlighted in terms of the thermal challenges with the existing approach. If all the thermal models and simulations are calibrated with this sort of an approach, it allows us to have interoperable models. Cage model from vendor A can be used with the transceiver model from vendor B. So that overall collaboration can happen much more seamlessly without the nervousness of thermal models not being correlated or the correlation going out of spec. The third thing that I wanted to talk about was having that greater visibility of the entire conduction path of the structure that is, or the assembly that is being analyzed helps a lot with thermal root cause analysis. It hasn't been long since I was a thermal engineer, and I completely understand the pain of debugging some of the thermal issues, right? So all the time we see some of the temperature of some of the ports in the I/O running high. We don't know if it's the thermal pad inside the transceiver. We don't know if it's the contact quality of the pedestal and the heatsink. We also don't know if it's the solder between the zipper fin and the base of the heatsink. So there's a lot of DOE that takes place, and it's a very tedious process to do that root cause analysis. With this sort of an approach, all we have to do is take the ideal structure function, compare it to the structure function of the part that is causing us the issue, and we can exactly pinpoint where the issue is coming from. So this sort of a calibration not only gives us that greater or improved calibration for our models for better correlation, but it also allows us to debug a lot of the thermal issues and the quality issues that we see with the everyday thermal testing that we do. The proof of concept that we had done was not in the application that typically Pluggable IO is used. It was just to show that thermal contact resistance is a value that can now be measured. In terms of our next steps, we do plan on having a white paper to basically talk about application-specific measurement and calibration, like actually inserting the transceiver in a cage and getting those contact resistance values. So that is one of the next steps that we plan on doing. For our call to action, we would want active participation from the different I/O vendors, because this gives us the path to have interoperable thermal models. But to have those interoperable thermal models, different I/O vendors, different transceiver vendors would have to work together to use this sort of an approach to basically calibrate their thermal models on one standard, which we could call it the thermal standard. And then this study at this stage was done with the active electrical cables. We do plan on expanding it to active optical cables, AOCs, coherent modules, and I mean, it can just be extended to any sort of transceivers that has a semiconductor in it, as Andras mentioned earlier. So that pretty much sums up what we had for today. Now we'll open it up for any questions in terms of what we highlighted today. Hi, Ian.
Yeah, Hasan, thanks for the presentation. Yeah, really informative. I just have a quick question about the test setup. So, like normally, what will be the accuracy of the whole test setup?
So that, based on some of the discussions that we've been having and based on the calibration for this particular proof of concept, we see a 99% accuracy in terms of the calibration that we get from this sort of an approach.
Gotcha. Thank you.
So can I add to that?
Absolutely.
So that 99%, it describes the calibration of the thermal model. So if you have a model in, let's say, a thermal CFD solution, and you want to calibrate that to the measurement, that will be the 99%. We can get it really, really close. When it comes to the actual measurement
yeah, that
accuracy.
will be my question about measurement error, yeah.
So the measurement itself, it has two error sources. One is the electrical measurement part. There we are very repeatable and reproducible, and the error is very, very small. So we can measure 4 microvolts of change with pretty good accuracy. When it comes to calibration, there's another calibration step when you get the voltage to temperature characteristics of your component. That depends on your thermal environment. That can be maybe 3% error maximum.
Gotcha. Thank you.
Sure.
Yeah, So my question is, thank you for the presentation. My question is, I see the call to action to expand the study to optical modules. And do you think your method will just be, can just transfer to measure the optical modules, because there's also like some optical components inside the pluggable optics, and your method will be like just a transfer to that one, or we need to take some extra consideration there?
So this is a great question. When you think of a light emitting component, let's say a laser diode or any sort of emitter, they, from our perspective, to be able to do the measurement, they are also a semiconductor device, which means they have this voltage to temperature sensitivity. So that, from that perspective, they're actually very, very easy to measure. The only thing you may want to think about, and you may choose or to take into consideration, or maybe not to, is the efficiency. So we have a lot of experience with high brightness LEDs. They can have like 40% efficiency, meaning that the power you measure electrically, it's actually only 60% is heating the chip. Now, for at least my experience with emitters used for communication, the efficiency is way lower. So you need to make a decision. Do you want to measure it? Do you want to ignore it? Or maybe do you want to approximate it?
Okay.
But
so that will still be a kind of a mix of measurement and kind of approximate estimation based on the component's efficiency, right?
So the temperature measurement is 100% accurate. When you create thermal resistance out of that temperature change, that's when you need to understand what was the power heating the component. So that's where, for an optical emitter, you need to either measure or understand the efficiency.
Okay, thank you. Thank you.
Sure.
All right, thank you. Thank you for joining us.
Thank you.
Thank you.